Aha. Okay, I think I found the unmute button. Let's see. Waiting for the stream delay. Hopefully I'm actually audible. Okay, cool. Okay, I heard myself, therefore this must be working. Cool. Thanks, Christian. Yeah. So, welcome to the Algebra workshop for Math1231 and 1231. Yesterday was Calculus, today's Algebra. For the first hour, I'm going to be doing the first two topics, which are subspaces and linear transformations. Not subspaces, vector spaces and linear transformations. And Jay is going to be doing the second half. That's going to work. I'm pretty much just going to go through problems rather than explicitly going through the theory of the course, but hopefully I should pretty much cover a pretty good representation of the theory from the course. So yeah, so let's just get into an example. Okay. Yeah. You can see the source of the problem. Fairly simple example. It's just about checking whether something is a subspace. In this case, it's not. And in this case, when you look at the question, something that you see straight away is that it doesn't really look like a subspace, because subspace would normally involve some kind of linear relationship between terms, but you've got a squared term there, and you've got a product of terms there. So you suspect that it's not a subspace. And you also suspect that it's not a subspace because the question says it's not a subspace. But so to prove it, we want to use the subspace theorem. And so the subspace theorem has three conditions. Zero vector, in this case, or existence of the zero, inclusion of the zero vector. In this case, it's clearly included because 0 squared equals 0 times 0. Multiplication condition, so if we multiply, in this case, each component by a scalar, then will it still be in the subspace? In other words, will that condition still be satisfied? In this case, you can see that it actually will be. And that's because if we multiply each term by lambda, say, then a factor of lambda squared will come out there, and a factor of lambda times lambda will come out on that side, so it will still hold. So the only thing that we have is the addition condition, the closure under addition. And so, how do you come up with an example? In this case, or in most cases, you can pretty much just guess anything. So before this, I prepared the simplest example. I didn't need to rub that out. But before this, I prepared the simplest example, I think, that exists. It's pretty much just two random vectors. You just need to make sure that they're not too trivial, otherwise they won't work. But in this case, we can pick u as the second standard basis vector, 0, 1, 0, and v is 0, 0, 1. And in that case, they're both in the set because this squared equals this times this, and this squared equals this times this. They're all 0. But when you add them together, the right-hand side becomes that, or the sum becomes that, and the right-hand side becomes 1, and the left-hand side stays at 0. So the sum is not in S, and so it's not closed on addition, and therefore S is not a subspace of R cubed. So in the proof, all we needed to mention was that one of the conditions broke. We didn't need to discuss anything about the zero vector or multiplication, because we're just proving that it's not a subspace. Nice. Okay, on subspaces, so that's the subspace theorem. I think this is the only time that I actually explicitly put a theorem in the slides. The reason I put it in the slides is because I have a random thought about subspaces that I've included there. So Isaiah makes the following argument about the subspace theorem. So we're considering a subspace that matches point 3. it's closed under scalar multiplication. Now, if it's closed under scalar multiplication, then we can pick some random vector in the thing, can multiply it by the zero scalar, or 0, that's the zero scalar. And then, because it's closed, this product must also be in the subset of the subspace, or the thing that we're claiming is a subspace. So that means that the zero vector is in the subspace. So that means if we have that 3 holds, then apparently 1 holds for free, because we can just multiply anything in it by 0 and get 1. Now, yeah, so the question is this argument correct? And I guess I'll give it one minute, because I think this is the kind of thing that you can really easily just answer in the chat if you think it's correct or not. Yeah. I guess it's not that instructive of a question, but it's good to think about exactly what these theorems are saying and what their limitations are, I guess. Not really limitations in this case, but yeah. Think about the theorems and take them above just applying them, I guess. Yeah. Feel as though it would be correct. It's a good feeling because it's very, very close to correct. I guess since no one said it now, I'll just say it. It is barely not correct. And that this argument is very close to correct, and the only mistake we made was saying for any v in S. And the breaking case is if there is no v in S. In other words, if S is the empty set. S is the empty set, then it is closed under scalar multiplication, kind of trivially. And I guess it is closed under addition as well, but it doesn't contain the zero vector. So, yeah. So point 1 is pretty much equivalently saying, or equivalently because of this fact, it's saying that it's non-empty. And the reason that this argument was incorrect is because it assumed that there existed any v in S. So does it depend on how you define scalar multiplication? I think it's either an axiom, a vector space axiom, or something that can be proven from the vector space axioms, that this is a thing for any vector in V. I don't remember which. I think anyone remembers the vector space axioms. Yeah, but I think it might be like you need to have V equals V, and then you can subtract v from each side, and you get a distributivity that equals 0. And so 0 times any vector must be the 0 vector. So I don't think. So I think this part is fine if that's what you were talking about. If there's something else that was circular, not sure where else it could be, then feel free to bring that up. All right. That was just a quick side note, I guess. Okay. So moving on from subspaces, we'll get on to at least another subspace. I don't know. Subspace and vector space are just the same thing in my mind. They're not the same thing. But we'll get on to another example of subspaces / vector spaces later on. A much harder one, but it's much harder, so I moved it a lot later. So now we're moving on to spanning sets, or span, or whatever. And so this one is just about some basic facts about span. So we're given a set of vectors. We're not even given a set of vectors. We're just saying that a set of vectors exists, constructed from 4 vectors. And we're asked if it can be a spanning set for R3. And I guess the basic idea is that that has dimension 3. so it can be spanned by 4 vectors. Or it can be spanned by any set with at least 3 vectors, given that the 3 vectors are linearly independent. But yeah, so 4 vectors, you can have one that is doing nothing much. So I think the best way to answer that question, you could probably do it without just by doing pretty much what I said. You just provide an example. In this case, a trivial one is we just give the first 3 standard basis vectors, and then this can be literally any vector, but yeah, 0 vector, why not? And this spans R3 because it contains the standard basis vectors. I think that's a good enough reason. Close. Okay, will all such sets S be spanning sets? Give reason. Funny how it says give reason. I don't know if that's because I copied the question down wrong or because they literally wanted you to give a single reason. Because usually it would say give reasons. But anyway. So yeah, if a set contains 4 vectors, or is constructed from 4 vectors, will it be a spanning set? And the answer is no, because they could be not a spanning set. And that's because they could, like, for example, all be the same. If they're all the same, then they won't span R3 clearly, because they'll just define a line or a point. If they're all the 0 vector, which is the example I provided, if they're all the 0 vector. So the span of S in this case would just be the 0 vector, or the set containing the 0 vector. And yeah, so I guess one random thing to note is that in this question, it defines S as a set. You might be feel a little bit dodgy about making them all the same thing, because then it's not really a set of 4 distinct elements. I think from the notation of the question, this construction would be allowed. Like, we're just saying that this set is just the same as that set with all 0 vectors. We're saying that they're the same, so that notation's fine. But if you want, you can just make them all like, I don't know, 1, 0, 2, 0, 3, 0, and 4, 0, and then they'll all be parallel, so they wouldn't span R3 clearly. Sorry, 1, 0, 0, 2, 0, 0, 3, 0, 0, and 4, 0, 0, which says that all lie in the x equals 0. That all lie in the, what's it called? The YZ equals 0 plane, the YZ plane or something. Not even that, they'd all just lie on the x-axis. I think that's what I meant to say. Yeah, they all lie on the x-axis. Sorry about that. So yeah. So there's many answers you can give. You can probably give an answer without even providing an example, but I gave an example there. Nice. Okay, part 3. Suppose S consists of the vectors. Okay, so now they're actually specifying some vectors. And they want you to determine a subset that forms the basis for R3. Now, so I guess as we know, or as is the definition of a basis, we need it to span R3, and we need it to be linearly independent. Or I guess, yeah, and the other thing about bases is that we can change one of those conditions to just having dimension 3. So in this case, we're just going to look for 3 vectors that are linearly independent. And to do that, we will write the matrix whose columns are the vectors. You can see that these just match up like that. And then to determine the linear independence relations between each vector, we will row reduce it. And yeah, this one's not too hard to row reduce, just 3 rows. Just 3 operations. But yeah, I don't trust myself to do it on camera, so I just put it on the slides. And that's what you get. And because these are all leading columns, that means that since the row operations kind of preserve linear dependence, that means that these three columns will correspond to linearly independent, like original columns in the matrix. So V1, V2, and V4 are independent, linearly independent. We can kind of see we got a what's it called? A non-leading column. Did I say non-leading column? I don't know if I've mixed them up or whatever. We see that we've got a non-leading column. In that case, it means that V3 is in the span of V2 and V1. So it's definitely not, so this set's definitely not going to be linearly independent because V3 is in the span of V2 and V1. And yeah. Cool. So I guess another way of justifying why this is a basis is because if we actually augmented this to be set to some other thing, if we augmented that to be set to some other vector, let's just say x, then we'd get some other vector x, let's just say x dash. And in that case, whatever x dash is, there'd be exactly one solution to this because there's three, there'd be a plane of solutions. There'd be a range of solutions. But no, there wouldn't. If we get rid of this, if we hadn't included that, then there'd be exactly one solution to that. And that's kind of how bases work. There's always going to be one solution. There's always going to be exactly one linear combination that equals any given vector. So that means if we get rid of that column, then we'll have exactly one solution. And that's what a basis is. Cool. Okay. Now this question is another basis question, but there's no numbers, or there's less numbers, much less numbers. So in this case, we're given a basis, and we would want to determine if these other things, if the other sets are linearly independent. Now, the first one is just a set containing one vector. And so, in order to be linearly independent, I guess you can think of it, since it's an R3, you can just think of it as that it is non-zero. Because if it's any set containing 0 will be linearly dependent because by the definition you could just have any scalar multiple outside the front of it, and that would add up to 0. So I just need to check that that's non-zero, or that u does not equal v. That's one way of thinking about it. It's just u does not equal v, because if it was equal, then that wouldn't be a basis. But another way of doing it, which is kind of more general in a sense, is to write up the definition of linearly independent, which is just that some scalar multiple of this, some sum of scalar multiples of each vector in the set is equal to 0. So in this case, it looks kind of dumb because it's not really a sum, it's just one thing. But in this case, it's just a scalar multiple of u minus v. And we want to check that the only solution is that we want to check that all one of the scalars must be 0. So a nice argument is just expand that. We get that. And then this left-hand side is a linear combination of u, v, and w. In this case, it's just u and v, I guess. But the coefficient of w is 0 for free. And since this equals 0, since this is a basis, it must be linearly independent, as I've said. So therefore, each coefficient of u, v, and w must be 0. W is already 0. The coefficient of w is already 0. We just need that coefficient and that coefficient to be 0. We just need that, yeah. So we don't need both of them, but yeah, from the fact that all coefficients must be 0, we get that must be 0, and we get that must be 0 for free. Or unnecessarily, but it's kind of obvious from the original equation that will be a solution. Yeah, I think that's a good way of arguing that question. We can also do the u equals v way. U does not equal v way. Okay, so for S2, we pretty much do the same setup, and hopefully it might be a bit clearer now exactly what we're doing to prove linearly independent. And In this case, we're again adding a linear combination, an arbitrary linear combination. We want to show that the only solution is when all the coefficients are 0. In this case, we just do the same thing. We expand it out and we collect multiples of the same vector, the same unknown basis vector. So we expand it, we get that because that's lambda 1u, lambda 2v minus lambda 1v, and then minus lambda 2v, lambda 2w. And then we use the same setup. We have a linear combination of u, v, and w, so all coefficients must be 0. So lambda 1 must be 0, negative lambda 2 must be 0, so lambda 1 equals lambda 2 equals 0. And that one we don't actually end up using. Okay. Now the third one, you look at it, you have these three thingers, and yeah, one thing I didn't really emphasize, but if you just look at them, and try to experiment with them, you kind of see that you can't really, the first two, you can't really force them to be 0 by just adding them up together. And the third one, if you just try some random stuff, then not even that random, you can just add them together and you kind of see that you have a u, a minus u, a w, a minus w, and a v and a minus v. And in that case, they all cancel out if you add them together. So by inspection, you get that if you have all coefficients as 1, then they'll add up to 0. So it's not linearly independent. If you were just doing this for the first time, then you might try the same approach as the other ones, because I don't think it's extremely obvious that it's linearly independent, especially if you've done the first two and you just want to get the third one done. In that case, what you'd get is something similar to that. You'd get something similar to that, but you'd get like lambda 2 minus lambda 1, lambda 3 minus lambda 2, and lambda 1 minus lambda 3 or something. And in that case, not that the only solution is going to be zeros. There's also going to be a solution of 1, 1, 1. And there's also going to be a solution of 2, 2, 2. Just in general, if they're all equal, then it will be a solution. You can try that, I guess. Cool. Okay. This question, which you can't see because of my app setup, was from 2020-1231 term 3. I think this was the last question, so I guess it was hard. But I guess it was hard in the sense that the last one was really annoying. So part A was like tick some boxes that verify this is a vector space, and I couldn't include that in the slides. I could have, but I didn't. So I just wrote V as a vector space. So I should actually introduce the question. But anyway, so we have a vector space, and we have ordered pairs A, B. So in this case, they're not explicitly calling them like typical column vectors or anything. They're just ordered pairs. And the weird thing about this question is that addition and multiplication aren't just component-wise. They're special. So in this case, to add A, B, and C, D, you do this weird thing where you have negative 3 plus AC in the first thing, and 5 plus B in the second one. And you can see the same thing for how they multiply. Looks pretty weird. And yeah, so the first few things were just ticking boxes that were like, addition is commutative, and scalar multiplication distributes over addition. They're actually like kind of annoying to prove, or very annoying to prove. But something like addition is commutative, it's not too hard to see, because if you switch these two around, then you'll just switch those two around. You'll switch those two around. And I guess the hardest ones to prove are the ones that actually relate these two. That combine them. So that's distributivity, I guess. Yeah, that's the only one that comes to mind. But the question doesn't ask you to prove it. In this case, the question was just, what are the additive and multiplicative identities? So to answer additive, or to answer these, I guess you open up your course notes because it's open book, and you check what an additive identity is. And in this case, oh, that's a lot of, there, look, okay. So an additive identity must satisfy, if you add it to anything, then you get a then you get the same thing out. So we pretty much just sub that into our definition of, given in the question, of what our special addition is. A lot of text, but we just substitute x, y. We could have just used CD again, but I just changed it to x and y for clarity. Let's get that. And I guess it's kind of given in the question that we can equate components just from the setup. And so we equate components. That gives x equals 3, and that gives x equals 5. X equals -5, y equals -5. And kind of see how that works. If we let c equal 3 and d equals -5, then we'll get a 3 there, so that will cancel out. And if we get -5 there, then that will cancel out. So we just get ab back out. And so if we add 3, -5 to anything, then we'll get the right thing back, namely the same thing. Can pretty much do the same thing for the multiplicative. In this case, it's a scalar thing that when you multiply it, it gives the same thing back. And yeah, this one I was kind of lazy with how I did it. So we pretty much just put that back in there. I cheated, I forgot to change them to muse, but whatever. And that's a typo. But yeah. What did I do here? Yeah, so pretty much you could solve it in the same way that I did properly. We actually equate components. But you kind of just look at these and you see, okay, if we want this to be equal to this all the time, then we need that lambda to be 1. Otherwise, that won't be equal. And lambda being 1 happens to make this stuff cancel out, because if lambda's 1, then it's -3 plus 3 and -5 plus 5. So if lambda or mu is 1, which I'm calling the same thing for some reason, then you'll just get AB out, A comma B. And that's good. Yeah, so I guess a better proof of that would be if mu equals 1, then this thing is true. And if mu is not 1, then we have a counter, then we can just chuck in any vector as a counterexample. So we could just chuck in 0, 0. Nope, maybe. Yeah, 0, 0, and then if lambda is not 1, then it wouldn't work. So we require that. But the only multiplicative identity is 1. I guess since it's a vector space, you can just say, okay, if I found any multiplicative identity, it must be unique. Yeah, I've kind of butchered this question, but I think the idea is pretty much that you just have to find the answer. In this case, I think it was just a maple question where you just put in your answer. But yeah, might be interesting to explore it a bit further, like I've done. Cool. Yeah, so find a real number such that this thing is linear. We just add the two terms and add k. So remember, a linear transformation is just where it preserves scalar multiplication and preserves addition. And so pretty much we just need to find some k that this holds. And in fact, in this case, in a lot of cases, you can just put in some random vector. Well, not a lot of cases. But in this case, since it's like already specified half of the formula, half of the transformation, and we're just trying to find some parameter, and just chuck in some random values and see which values of k it forces it to be. And one thing that might be nice to think about is the additive identity. What happens if we sub it in? If we sub in the additive identity, it's not hard to see that, or you can prove to yourself that the additive identity, when you sub it into a linear transformation, it should always give the additive identity in the output space. So I think the 0 vector is the same thing as the additive identity. So when you plug in the 0 vector into the transformation, you should get the 0 vector out. And that is a consequence of whatever you want it to be. But I guess it's a consequence of scalar multiplication, or like adding a negative or something like that. But in this case, I pretty much just prove it on the spot anyway. So we have an additive identity, so that means that when we add it to itself, it's the same thing. And by linearity, we can split it up into two thingers. And so we have this equals 2 times itself. And so that must be 0. So we just do that, and then we get k equals 2. So that's how we find the answer. Now, unfortunately, this question asks you to explain it, which is probably why it was the last question. Actually, I don't know. I don't know what was the last question. Actually, it's not necessarily difficulty order, so it doesn't actually need to be hard. But anyway, it asks you to explain it, and that is very not fun. And pretty much what you have to do is just do the thing where you use this, we use the transformation theorem. What I did was to check that it's linear, was to do that. Is that what it suggests in the course notes? I don't know. Someone can check that if they want. But yeah, this does check that it preserves multiplication and addition. But I don't know if that's only a thing that's supposed to be used for the subspace theorem. If it is, whoops. If it isn't, good. But yeah, so this thing's kind of absolutely horrendous. Not that bad, to be honest, but it's quite a lot of stuff. But yeah, pretty much what we do is just apply the definitions. So we just apply the weird definition of multiplication, apply the weird definition of addition. So we have, we add the components, subtract 3. We add the components, add 5. I don't know, I did it in a kind of weird order. And then we apply this transformation, how we defined it. So we just add 2 at the end. And then I guess the hard part is checking that these two things match up. So you just have to match all the coefficients, and you can see that it kind of works. If you just compare them, I'm not going to do that now, but yeah. And then that's what we want it to be. That was cool. Made like a cloud. Anyway, that's how that worked. Yeah, I don't know. You can check the course notes if that's a valid way of doing things, or a way that it's valid, but I don't know if they'll allow it. Anyway, that's what I did. Yeah. Yeah, I don't think there's much more to that question. All right. So back to a normal question, I guess, a written question. So this one's asking if there exists a linear map. And we can see it's kind of hidden in the question. We're given that this thing. So V3 is a linear combination of V1 and V2. And that means that it would be good to check that this transformation would preserve addition and scalar multiplication under the transformation. So namely, we're checking if T of V3 is going to be 3 T of V2 plus T of V1 plus T of V2. So we just check it. So we're just checking this equals this, where this step, where this is just by definition, I guess, with the transformation applied. This is by linearity, or assuming that it's a linear map. And so we're given all these values in the question. We're given that in the question. We're given that in the question. That in the question. We're given that in the question. So we just sub them in and see if they're the same, and they're not. So no linear map T exists. Yeah, not too much to that question, I don't think. If they do end up being the same, then there possibly is a linear map, in which case you'd probably guess one. And yeah, if it works, it works. And if it doesn't work, then yeah, if it works, it works. If it doesn't work, then try some other spans and see if you can prove it another way. Try and find some other linear combinations and see if you can prove it that way. I guess one thing that could break it is if there's like two vectors that are parallel. In this particular case, if there was 2 vectors that are parallel, then they would have to give the same output. But then you probably wouldn't get a condition like this. Okay, there's no point speculating. Well, there is a little point speculating, but not now. Yeah, I think that's all that I'll give to that question. All right. So we're back to bases and subspaces for some reason. Anyway, find a basis. So we're given this very weird looking, not weird looking matrix, kind of trivial looking matrix because 2 columns are the same and 2 rows are the same. A lot of things that are the same. Anyway, to find a basis for kernel of M, we want to find the solutions such that we want to find the values of x such that it gives a 0 vector. And if we remember how scalar multiplication works, matrix vector multiplication works, if we have 1, 2, this will just be vectors to be 0, then they just need to be opposites of each other, which is kind of obvious because it's the same vector. Nice. Okay. Basis for image of M transposed. Let's just write M transposed by definition of transpose, and want a basis for the image of this. We just want to find a basis for all possible linear combinations of this thing. So I guess so when this is multiplied by something, what can it end up being? And if we do the same thing as before, where we multiply it by AB, we get exactly the same thing. So it's A plus B. But not exactly the same thing, but we get that. 2B there because yeah, it was A plus A11 plus B22, which equals that. Equals that. And in that case, it's just a multiple of 1, 1 times some random, not random, times some scalar multiple. So as a basis, we just have that. So this one is just going to be that. Nice. Okay. So question is kind of weird. It asks you to give a geometric description. I guess that's why I included the question, because I don't know, in case you're asked on it what a geometric description is. But this one doesn't really make any sense to me, so feel free to ask about it. Kernel of M is just this thing. This is a basis for kernel of M. So kernel of M is just the whole line, right? My mirror is flipped, but it's just the whole line y equals negative x. So it's just the line. That one's a line. Image of M. We didn't actually compute image of M. We computed image of M to the T, M transpose. Why they asked a different one now, I don't know. But the image of M is just going to be we were adding the same thing together, adding the linear combinations of the same thing together. So it would just be linear combinations of 1, 2. This thing is just going to be of the form. It's just going to be any vector of the form that is in image of T. Or in other words, 1, 2, it forms the full basis of the image of M. And in that case, it's a line. I don't know what the point of that question was. I don't know if you're supposed to find some relationship between them, but there's not really one. But they're just both lines. There's one thing you can think about if you're interested in how linear transformations really work on the plane. You can think of it as you have a linear transformation that maps everything onto this line, everything onto this line. And in particular, this line y equals negative x, all of this stuff gets moved to 0. So any vector on here gets moved to 0. But in general, vectors just get moved onto that line. So this line is image, this line is not imaginary part image. Anyway, yeah. Cool. Okay. The question basis is just the column space. No. I'm not sure which question that was for. Presumably this one, because it's been a while since I was on another question. I don't think I missed too much in the chat. But let me know if this is the wrong question. So I guess the Yeah. So I think what you're going for is that the column space of a matrix is the same as the image of the transformation of that matrix. So I guess in that case, the column space of this matrix is just going to be spanned by 1, 2, so it's just that's the column space of the matrix. And the image is the same thing, the image of the matrix, which is kind of a shorthand, or it's correct definitionally, but it's kind of a definitional shorthand for the image of the transformation representing M, or represented by M. So yeah, that's I think the idea. The basis isn't necessarily the column space because the columns don't necessarily have to be linearly independent. Oh yeah, and another thing is the column space is, I guess pretty much by definition, I think it's the definition, is the span of the column vectors within it. So they're all the same thing pretty much. Image, span of the columns, and column space of the matrix. Let me know if any of that was confusing or if I was on the wrong question. All right. And there's only 15 minutes left. Okay. Spoilers. So this question was in the 2021, so an online thingo last year. So yeah, we have some linear transformation. We don't actually know the domain, we just know that it's r to the n where we don't know n. But we will shortly know n. So it's given that the image is the span of this vector and the nullity of t is 5. Nice, coincidentally, it's kind of similar to the last question. The image is kind of trivial, it's just a line. So the image, the dimension of the image is just 1, also known as the rank is 1. The rank is 1, the nullity is 5, and the domain space, the dimension of the domain is r to the n. So by the rank nullity theorem, n is going to be 1 plus 5, which is 6. Oh, there. Cool. Find a possible matrix A. So yeah, I'm kind of going quick, but we're just finding a matrix such that its image is 731 and its nullity is 5. And I guess if it's in R6, then both of those must be satisfied, or that one of them implies the other. But we'll just do it. Yeah, so we just want to create a 3 by 6 vector because the 6, the input dimension is 6, and the dimension of the input is 6, and the dimension of the output is 3. So in this case, the most trivial answer, or one of the most trivial answers, is to just do that. So we'll check that the image is 731. So we can see that if we put anything in, any vector in, so any vector a, b, c, d, e, f, this will give us a multiple of 731 because it would just be 731 times a. Yeah? So, yeah. And which vectors will give us 0? If we let a equal 0, then these can be whatever we want. B, C, D, E, F can just be anything. Literally anything. As long as a is 0. And then this thingo will always just map 0. So our nullity is just the size of the vector space such that all of these are 0. And I guess there's 5 parameters. So it has dimension 5, which is what we want. The nullity of t is 5. Might have been mixing up my terminology, but hopefully everything was clear anyway. Yeah. I don't know if that example was just too out of thin air, but anyway, that's what I did. Let's skip that. This one's kind of, okay, let's skip some other ones because this one's, yeah, whatever, let's do it. Okay. So, yeah, another one about geometric interpretations. I feel like this is kind of potentially likely to show up just because kind of hard to just read the book and understand it. Because like in the exam, they probably won't just chuck stuff in where you can just open the textbook and just read the procedure and it just tells you how to do it. So I think geometric transformations is kind of a thing where you can't really do that as easily. But anyway, in this case, it's just a transformation that rotates it by pi on 6 radians, anti-clockwise about the origin, and doubles its length. And to find the matrix, we're just going to use the matrix representation theorem, which says if we find where each standard basis vector lands, then we know, then we can write a matrix for the transformation. In this case, it tells you where the first one will land, just so you can check that your answer is correct. So the way that I've set it up, or the way that it's been set up, is that we kind of write it in, we kind of rewrite the standard basis vector in a form like this, which just means that it's really easy to apply the rotation. So we pretty much just add pi on 6 to each angle in each trigonometric function, and then we just evaluate it and we get what we want. So in this case, we just add pi on 6 to 0. In this case, E2, since that is going to end up being 0, and that's going to end up being 1. Oh, that's correct. So we can just add pi on 6 to each of these and get that. And so to get the matrix, we just put these columns together. So we just, that's the first column, that's the second column, and then we have our answer. Cool. Yeah, I guess something interesting is that rotations are linear. But I won't get into that too much. It's not obvious that rotations are linear. It's pretty much because we're treating this as almost the definition of rotation. But we can also think of it as like you add these things, you add these things independently of the scalar multiple at the front. So it's closed in that sense because you're pretty much just adding this thing and this thing. You can kind of treat it as a vector space where the two components are the angle and the magnitude, and they're kind of independent of each other. So that's why everything works. That's why it's a linear transformation. So yeah, the matrix representation theorem assumes that it's a linear transformation, which you're given. But yeah, it's just kind of interesting to think about that. That's not that interesting. How much more do I have? Okay, I have 9 minutes, so I'll just do the last two things. And the last one's kind of long. So this one, not a very interesting question, but it's about a maple output. So yeah, this one's not too bad. So in the maple session, they input a matrix and they solve when it's equal to 0. We want to see, is it linearly independent? And remember, I've done it a few times, I think, maybe once today. Is linearly independent means that any linear combination any linear combination being equal to 0 forces all coefficients to be 0. Now, this is just another notation for solve that. Well, it's the maple notation for solve that, because the 0 vector of 4 is just that. So, and this is just linear combinations of these columns. So I guess the key idea is that linear combinations of columns is just the matrix of those columns multiplied by an arbitrary vector, and that creates all linear combinations. So that means that if we want to find the linear combinations of this, then we can just multiply it by an arbitrary vector. And if we want to see when those linear combinations are 0, then we solve for when this multiplied by an arbitrary vector is 0. And in this case, we get that. So x can be, so in this case, we can get some non-trivial solutions, or some non-all-zero solutions. In this case, we can get a solution like 0, -4, 1, 1 by letting underscore t4 being 1. But we can also let it be anything and we'd still get a solution. So in that case, so yeah, pretty much this is just solving for the kernel of this set by row reducing the matrix. And since the kernel has dimension of 1, because there's one parameter, it's not linearly independent. The set is not linearly independent. The basis for kernel of A, which is just a basis for this thing, because this is pretty much just a set encoded by one parameter. So the basis is just that. Very nice. If there were more parameters, then you just create a new basis vector. So like if there was a t1 in that component, and 2t1 in that component, then you just have another thing that was like 0, 1, 0, 2. Not like that. If you had more parameters, you just add more basis vectors. Like that, if there was another parameter then. Yeah, basis for a kernel is fairly simple in that way. Or at least from a maple session, because how the maple session would have computed it, I think, is pretty much just do your Gaussian elimination thing on the 0 vector, and then do back substitution to get those. So this pretty much is the back substitution for free for you. That's pretty much all it is. Okay, last example, I'll go through it very quickly, because this one's kind of interesting. Okay, so we have a vector space of dimension 95, and it has two subspaces. So this is the hard subspace thing that I was talking about at the beginning. We have two subspaces. One of them is U, dimension 45, 47. One of them is W, dimension 56. And we're thinking about the intersection of U and W. And yeah, so in the question it asks you to, this was last year, I think. 1241 Q5 2020. So it asks you to prove that the intersection is a subspace. I think there's actually a problem in the course notes that goes through proving that an intersection of any two subspaces will be a subspace. But yeah, let's just do it. So for all x in. So we're proving that S is a subspace, so we're showing that it's closed under addition and multiplication. So in this case, we'll say for any two vectors in S, we're going to argue about their sum. So I guess from the question, we know that they're both in U, and so since x, this is crap. Not good notation. I made the boxes way too small, but we know that x and y are in U, which is a vector space. So since it's closed under addition, x plus y must also be in U. Similarly, just the same thing, but for V, it's a vector space, so x plus y is in V. Therefore, x plus y is in U, it's just xv, and hence in S, I guess. I don't know what the question. In the actual question, there were like drop-down boxes, because this was on Maple TA. But yeah, this shows that S is closed under scalar addition. Not scalar addition, is closed under vector addition. I won't write that. And similarly, it's pretty much the same thing. For all x and S, x is in U and V. That's terrible. That's not good notation, but it's in both. And therefore x is in. But the idea is that we're not talking about the intersection. We're talking about them both separately. In this case, the question was kind of shorthand. Kind of did them at the same time. Therefore, x is in U and V, and hence it's in S. This shows that S is closed under scalar multiplication. Using the subspace theorem and points 1, 2, and 3, we included S as a subspace of V. Because, yeah. Yeah, I guess point 1 is kind of important. For it to be a subspace, it needs to be a subset of a known vector space. That's almost always absolutely given, but in this case, they were explicit about it. Okay, perhaps you can see down the sidebar that there's a lot of stuff to go. So I'll go through it very fast. But the next part of the question was find the greatest possible dimension and least possible dimension of S. And as an extension question, I set out to prove it because it's non-trivial, very non-trivial from what I found anyway. Maybe I'm just bad. So, greatest possible dimension of S. So if we want to maximize the intersection of two thingos, then we'll just make one a subset of the other. So we'll just chuck as much of U into W as possible. So pretty much just make U a subset of V, U a subset of W. And I guess a proof, so if we make U a subset of W, then the intersection will just be all of U. And so U will have dimension 47. So yeah, that goes, so that means, so this is kind of proving an upper bound. How did I make an arrow? This is proving an upper bound because the dimension of an intersection will be less than the dimension, well, this is a subset of this, so the dimension will be less than this, which is 47. So it's a maximum 47. And so we've proved an upper bound, and now we just quickly provide an example. So we just let U be the first 47 standard basis vectors, let W be the first 56, and then the intersection is 47. So we've managed to achieve that upper bound, and hence it's actually, so it's not just an upper bound, it's something that we can actually achieve, hence it's the maximum. So I guess a maximum can be defined as an achievable upper bound. So that red thing, I just quickly justify. Since this is a subset of this, we can extend the basis of this to a basis of U. And you can see the notes. And it's really simple what you do. You just, to extend a subset to a set, you just add things that aren't in the subset right now. And just keep adding them until you get to the basis, until you get to the full set. That's why that is less than that, because if you add vectors and it stays as a basis, then it must have an increased dimension, because dimension is the size of the basis of a basis. So yeah, that's a proof. Nice. Okay, the next part is much harder, or quite a bit harder at least. So to minimize the dimension, oh no, I've hit 1 o'clock. Wouldn't it be W instead of V? Probably. I found it really confusing why they use U and W. I guess it's because V is the big vector space. But V is after U in the alphabet. Where's my mistake? I think that slide's fine. This slide's wrong, but that should be V, right? That should be W. Yeah, if it was somewhere else, whoops. Anyway. So if we want to minimize the intersection, then in this case we kind of spread them out as much as possible. So we don't let them share anything. And since there's only 95 dimensions to give out per se, we give them, so I guess the example makes that clearer. We give them all to U, and then we give as many to W. So this starts from 48 because we avoid sharing our standard basis vectors until we have to, and we end up having to share 8 because once we've given them all out, or once we've done, yeah, that just ends up being the computation that we get. So that means that the dimension is 8, so we can achieve 8. Now we kind of have to prove it, and that's what the hard bit is, and I'll go over that in 1 minute, which this does not deserve. But anyway, proof. Let B be a basis for this, and we extend it to become a basis for U. So we kind of have a kind of Venn diagram where A is a basis for U, but excluding stuff from the intersection, and B is the intersection. C is from W, but excluding the intersection. And then, so this is going to be very, very hard stuff. Not very hard stuff, but very abstract stuff, I guess, very quickly. But you can look at it later, or you can just ignore it because it's not very important to know, but it's just interesting to me and hopefully to you. So just by how we've defined it, the size of A from that Venn diagram is going to be the dimension of U minus the dimension of the intersection. Just because we're extending it, so we extend it until it's the dimension of the higher thing, so that's why it's that. B is that by definition because it's just a basis for that. B, and that's the same thing. That means that because they're all disjoint from each other. Yeah, they're all disjoint. I guess A and C are disjoint, which you can prove, which I didn't really prove. But I don't think you actually need it, because it will end up being proved a bit later. But anyway. So if we can prove that they're disjoint, I guess, and if we can prove that this is linearly independent, this set is linearly independent, then we know that its dimension must be less than the overall thing. If we prove that it's linearly independent, then it has smaller size than the dimension of V, because any linearly independent set will have a smaller size than a spanning set, such as the basis for the whole set. It's going to be less than that. And yeah, I've gone over time, but to prove that it's linearly independent, we suppose that some linear combination of the sum 0. This thing is going to be in W because this is all in W, so any linear combination must be in W since 0 just doesn't matter. This must be in W. It's also in U by construction since all of the AI were in A and A was a subset of U. A was a subset of the basis for U, and so that means that U is in this intersection, so it's in span B, because B was by definition that. And it's also in span A, because that's how we defined it, I guess. It's very similar to that claim. Anyway, since A union B is linearly independent, that means that the intersection of their spans is 0, and I guess since they're disjoint as well. Okay, that thing you can very quickly justify just by the algebra. If their spans overlap in a non-zero place, then they're not going to be linearly independent. Okay. So that means if U is in span A, U is in span B, and the intersection is 0 vector, then U is 0. So all A, alpha I is 0. So all of these are 0. And that means that since that is a linearly independent set, B and C is a linearly independent set because it's the basis for W. That means all the coefficients are 0. And we're done. Okay, I'm done before 105. So hopefully Jay won't be too angry that I went over time. But yeah, I guess the final remark is that you can Google that. That's pretty much what this question required. The question didn't actually ask you to prove it, but I just thought it was quite interesting and quite hard to actually prove it. That's why I showed it to you. Yeah, hopefully these slides should get uploaded to the website or something. So yeah, you can read through this. Hopefully there are no mistakes. Let's look at the fill in the blanks question. Oh yeah, all my V's should have been W's, I think. Yeah, all of them should have been W's. Okay. Yep, thanks for that. Yeah, okay. I'm done. Feel free to ask any questions while Jay gets onto the stream. How does the stream even work? Do I need to actually explicitly end my stream before Jay can hop on? I don't know. Okay, anyway, I'll stop my stream. Thanks. Hopefully, yeah, stay for the next hour. Cool.
Hello. Can you guys hear me or see the screen? Yep. Can anyone let me know in the comments whether the stream is working at the moment? Yep. Okay, great. Okay, so I'll be going through the next parts of the algebra section, which includes linear transformations and also eigenvectors and eigenvalues. Okay. So the first thing I'll start off with here is that we have linear transformations and like what it means in order for some sort of mapping T to be a linear transformation. So in order for this mapping T from V to W to be a linear transformation, it needs to preserve addition and scalar multiplication, which means it has to satisfy this addition condition, where if V and V dash are some vector in the domain V, after you evaluate it, you have to be able to rewrite it as TV plus TV dash, where TV and TV dash are elements of your codomain W. Okay, and also you need to satisfy scalar multiplication, which means that if you take T of a scalar times the vector V, after you evaluate it, it has to be able to be rewritten as having your scalar on the outside of TV. Okay, so Let's have a look at an example here on how to prove whether something is a linear transformation. We have a slightly more exotic example here where you have polynomials rather than just vectors, but I'll explain what that means. So prove that the function t, sending you from the polynomials of degree 1 with real entries or real coefficients to R2 is defined by Pp equals to P0, P1. So I guess I'll briefly explain what this means. So P isn't just a number, it isn't just a vector, it's kind of like a particular function. So this P here really could be expressed like this. It's some first degree polynomial where a and b are coefficients, the scalars, and you have x to the power 1. Yeah. And then P0 would mean evaluating it at 0. Okay. And okay, yep. And P1 would be like evaluating it at 1, for example. That's what these P here means. Okay. And so in order to prove that it's a linear transformation, we need to show two things. We need to show it preserves addition and that it preserves scalar multiplication. Okay. So our first step here is to show that it preserves addition. So let P and Q be two different polynomials from the set of first degree polynomials. Okay. Then T of P plus Q would be equal to the function P plus Q or the polynomial P plus Q evaluated at 0 and the polynomial P plus Q evaluated at 1. But if you recall how functions work, if you have P plus Q, like you add two functions together and evaluate at a certain point, it's the same as just evaluating it individually. So then you have P0 plus Q0, P1 plus Q1. But then by the linearity of vectors, you can split off this vector different vectors. Like this, right? Then you have P0, P1 as one vector, plus Q0, Q1 as another vector. But then by definition, P0, P1 is just TP, and Q0, Q1 is just TQ. And so that has preserved addition. Okay. And now the next condition is to say that it preserves scalar multiplication. So again, we let P be some first degree polynomial from PR, and lambda be some scalar from the real numbers. The reason why we chose real numbers is because the polynomial here, they indicate it is real numbers. Then T of lambda P would be the function lambda P evaluated at 0, the function lambda P evaluated at 1. But then again, by the linearity of polynomials itself, you can take the lambda out, then you have lambda times P evaluated at 0 and lambda times P evaluated at 1. And then by the linearity of vectors, this lambda can be taken out. And so you can take the lambda out and you have lambda times the vector TP. Okay. And so in that case, we have shown that it both preserves addition and scalar multiplication. And so T is a linear map. Okay, because it has preserved the two conditions. We have a look at an alternative proof here. So in the previous question, we did both addition and scalar multiplication one by one. But there is a slightly faster method, and the method is to, rather than checking out whether it preserves addition and scalar multiplication individually, you check out whether, I guess, it preserves linear combinations, right? So you take some vector v1 and v2 from the domain, and then compose it with some scalars, add the two together, and if this transformation here can be evaluated and then rewritten as lambda 1 of tv1 plus lambda 2 tv2, where tv1 and tv2 are vectors in your codomain W, then you can also claim that it preserves or that's linear without needing to do the two steps separately. You kind of combine both steps into one. Okay, and of course we can generalize this above, I guess, method into not just using a linear combination of two vectors, but I guess as many as you want. Yeah. So let's have a look at an example of using this method instead. Okay. The mapping T of V to V is defined by some function in the codomain, in the domain V, and then you have T of the function theta equals to f dash theta minus f pi and 2 minus theta, where theta is some real number. Okay. So again, from the above problem, we can do this. Oh no, sorry. Even from the above problem that we did initially, recall that when you have functions, function f plus function g evaluated at x, it's the same thing as if we evaluated it individually. And again, lambda f times x is the same as lambda fx. This is by itself just a linearity of functions. Okay. And it's also linearity of differentiation. So if you have a f plus g dash x, again, it's the same as if you evaluated it individually. So a f dash x plus g dash x. These will be important in this proof here. Okay. So to do it this time, rather than showing that it preserves addition and scalar multiplication individually, let's try to do it in one go by, I guess, showing that it preserves linear combinations. Okay. So you take P and Q as elements of the domain V, lambda 1 and lambda 2 as scalars from the set of real numbers. Then what that implies is that Tp theta equals P dash theta minus P pi and 2 minus theta. This just comes from the definition of T f theta, dash theta minus f of pi on 2 minus theta. And so really here we're just replacing f of p. And similarly here we're just replacing f of q. I'm just in my first line stating what it means for p and q to be in this domain V. Okay. Then consider the linear combination of p and q composed of the scalars lambda 1 and lambda 2. Okay. If we have this, then again, we replace this entire thing for f. So we have this thing dash theta minus this thing pi and 2 minus theta. Okay. But then again, by the linearity of differentiation that I showed you in the previous slide, this can be taken out and basically the derivatives are evaluated individually. So you have lambda 1 p dash theta, that comes from this, and lambda 2 q dash theta, that comes from this. Okay. And then this next part is by the linearity of functions, or like how functions are defined. So if you have one function add another function evaluated at pi and 2 minus theta, it's the same as evaluating each function individually at pi and 2 minus theta. So you have lambda 1 p of pi on 2 minus theta and lambda 2 q of pi on 2 minus theta. Okay. Then in this next line, now that you've split everything off, we can regroup them. Okay. So you purposely regroup the p terms back together. So this term and this term here to form this term here in the brackets. And you group this term and this term together to form this term in the brackets. And the reason why we do so is because if you have a look at it more carefully, after we factorize out lambda 1 from this term here, you'll be left with what Tp theta is defined as. Hello, sorry about that. I think my Wi-Fi dropped a bit. I changed over the hotspot, so it should be fine now. Okay, yep. So in case I was cut off in the last bit, I was saying that, and so this part here is Tp theta, this part here is Tq theta, and so we're done because we have shown that it has preserved, I guess, linear combinations. Okay. We have another example here. Show that the map T from R2 to R3, defined by the thing below, is not linear. Okay, so the past two examples was to show that it is linear. This is to show that it's not linear. The easiest way to do so is to just use a counterexample. Okay. A little tip that is here is that if the transform vector has a non-linear component, so in this case, this part here, because it's not just x1 plus x2 or some linear combination of x1 and x2, it's literally x1 times x2, then most of the times this would not be linear. Okay, and so it's not necessarily a proof, but it's just a good way for you to check whether or not you're on the right track. Okay, so how are we going to choose a vector to show that this is not linear? Okay, in this case, we're going to consider the vector v11. Okay, why did we choose 1, 1 in particular? If we go back, you have x1 plus x2, that will give you 2. x1 times x2 would give you just 1, because 1 times 1 is 1. and negative x2 would give you -1. If you think a bit forward into what will happen once you try, for example, compose it with -1, then what you'll get here is you'll get -1 in this second component, but when you're putting it in the inside, you'll have -1 times -1, and that will still be 1. So the whole point why we trace the 1, 1, and why we trace the scalar -1 is mainly because of this second component here that's not linear, right? Because if we take -1, -1, that would not be equal to 1, 1. Okay. Hopefully going through this example will make a bit more sense. So we chose v equal 1, 1. Then that means T of v would be 2, 1 minus 1. Recall that T of v is v1 plus v2, and then v1 times v2, and then negative v2. So we have 2, 1, -1. Now, if this map was linear, then this here would be true, correct? Because if you have the scalar on the outside or the scalar on the inside, it shouldn't matter. It should preserve scalar multiplication. So we're going to use this fact to show that it's not linear. If you have the scalar on the outside, then you would get -2, -1, 1. On the other hand, like I said before, if you have the scalar on the inside, this middle component, you would get -1 times -1. And that'll give you 1. And so that would already disprove it, because this vector here would not be equal to this vector here, because even in the second component, you have -1 and 1, that's not equal. And so it's not equal, so this here is false in this case. And so you can claim that it does not preserve scalar multiplication, and so T is not a linear map. Okay. So the whole point why we trace this vector, again, I'll repeat one more time, is to, I guess, abuse the fact that this second component here is not linear. And so you would know that -1 times -1 is not the same as negative of just 1 times 1. And so we use that fact to prove that it's not linear. Okay. The next thing to have a look at, after, I guess, just proving how some maps are linear and how some maps are not linear, we're going to have a look at matrices, and I guess how that relates to linear maps. So matrix multiplication is a linear transformation. So for each m by n matrix A, the function t that sends you from Rn to Rm can be defined by t of x is equal to a times x in terms of a matrix times a vector. Okay, and that basically leads us into the next theorem here, which is the matrix representation theorem. That basically says that we can represent some sort of mapping just by some matrix A of an appropriate size. Okay. It furthermore, in this theorem, says that every jth column of the matrix has a property where it can be given by just T of Ej, where Ej is the jth basis vector. So if you recall what basis vectors are, E1 would be 1, 0, 0, 0, blah, 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 all the way to whatever that last position is. E2 would be 0, 1, 0, 0, 0, 0, 0, all the way to the last position. And basically with every single, I guess, basis vector up, this number here just dictates where the 1 is. So Ej would just be having a 1 in the jth position. Okay. And what this is saying is that if you evaluate T of Ej, then every vector you get out of this will become the columns of your matrix A. Okay. And we'll see an example of this soon. So the example we're going to have a look at is, let C be some vector C1, C2, C3, and it's a fixed vector in R3. The function T sends you from R3 to R3, and it's defined by C cross product X, where X is some vector in R3 as well. Okay, and yep, just like I said, C is C cross product X. Okay. Find the matrix C, which represents T with respect to the standard basis for R3. Okay. So here they're asking you to find what is the matrix representation C for this transformation here. Okay. So we're going to use the theorem that we just learned, and that was if you evaluate the transformation or the mapping T at all the basis vectors E1, E2, E3, it will basically return you the vector that fits in as that particular column of your matrix representation. So we have your three basis vectors here, E1, E2, E3. T of E1 would be this vector here, this is your vector C, cross product with your vector E1, correct? Then if you recall how to evaluate cross products, it's basically taking the determinant and then putting, I guess, all the basic vectors in the first row, and then your first vector in the second row, and your third vector in the last row. And then evaluating the determinant. Then you have E1 of C2 times 0 minus 0 times C3, get that, minus E2, C1 times 0, 1 times C3, and then E3, C1 times 0, 1 times C2, which in the end gives you this. Because remember, E1, E2, E3 are the spaces vectors, and so it's just going to be 0 in the first position, 0 in the first position, C3 in the second, and negative C2 in the third. Okay? That was for T of E1. Then if you did the same thing with T of E2 and T of E3, you would realize that these would be the vectors you get. Okay? That would be quite simple. You just plug in E2 and E3 into this exact same methodology here. You would just take C1, C2, C3, cross product with 0, 1, 0 instead. That would be for T of E2, and C1, C2, C3, cross product of 0, 0, 1 instead for T of E3. Okay. And once you evaluate all that, then you can just use the matrix representation theorem, which basically, like I said before, takes this first vector, slots into the first column, the second vector slots into the second column, third vector slots into the third column, and there you have your matrix C. Okay? Good. All right. So that was basically a method we can use to represent our mapping T instead with some sort of matrix C. So what this basically now means is that if I want to transform some vector x, it's the same as if I just took my matrix and multiplied it by my vector x. All right. Another example here to think about is its geometric application as well. So let T be a mapping from R2 to R2, which rotates a vector pi on 6 anti-clockwise about the origin, and then doubles its length. Show that T of E1 to the first basis vector is root 3, 1, where E1 is 1, 0, and find the matrix representation A such that Tx equals to Ax. Okay. So the first thing to note here is, I guess we're given a diagram here as well. For this first question, they claim that T of E1 is the same as T of 1 cos 0, 1 sine 0, and then they somehow transform it into this thing here. Okay. So let's briefly explain how they even got this to begin with. Okay. You did this example the first hour already. Okay, if that's the case, then I'll skip over this example. Okay. Okay. Yeah. If it's already done, then you guys can just either look at it in the lectures or like if you forgot. But for now, I'll just move on to the next thing, then kernels. All right. So kernel or null space definition. The kernel of a linear transformation T, sending you from the domain V to codomain W, is the set of all values in the domain V, which map to the 0 vector in the codomain. That is, the kernel is a subset of V defined by the kernel T, where TV equals to 0. So, and similarly for the matrix A as well. So what the kernel basically means is it's a subset of your domain, where if you take a particular vector out of the kernel and I guess take T and transform it against V, it will send you to the 0 vector in the codomain. So it's saying it's just any vector V in the domain where T or V sends you to the 0 vector in the codomain. Okay, that's what the kernel means. It's a set of all vectors that does that. Okay. The geometric interpretation of a kernel. Okay. Suppose B is a non-zero vector in R3 and consider the projection map R3 to R3, for some map T. And you define Tx as basically the formula for projections. X dot B over the like the norm of B times the vector B. Okay, you're just projecting. So if you recall, this is the same as just projecting X onto B. Okay, you may assume that T is linear. Describe geometrically the kernel of T. So the kernel of T would consist of any vector x dot b equals 0. Why is that the case? Okay, remember the kernel is any vector, I guess in this case x, that would send you to 0 in the end. Correct? The 0 vector in the end. Okay, or just 0. In this case, it would just be the 0 number in the end. Okay, or the 0 vector. Just put 0 here. Okay. In order for this to be true, the only place where that can happen in this transformation here is in this x dot b, right? B is a non-zero vector, so you can't really expect this b here to be the reason why it sends you to 0. Clearly, the denominator can't be the reason for why it sends you to 0, because even having 1 over 0 wouldn't give you 0, that would give you undefined or infinity. So the only place in this entire projection formula here that could potentially send you to 0 in the codomain would be this x dot b here. That's where they get this line from. Okay, the kernel of T would just be any vector where x dot b would send you to 0. Yeah. But what does the dot product mean geometrically? Well, it means that your x here, or whatever x it may be, it's always perpendicular to this fixed vector b. Right? Recall that if your dot product is 0, it means that you're perpendicular or orthogonal. Right? So that means the kernel would be all vectors that are perpendicular to your fixed vector b. Furthermore, you should also recall that the kernel must at least contain a 0 vector. And so that means, if you think about it geometrically, what happens here is that your kernel is just the plane that passes through the origin and it's normal to b. Okay, so if I try to draw a quick diagram here, it would be like this particular plane here, for example, where this here is your vector b, and then any other vector on this plane would be a potential vector x, because everything here would be perpendicular to your vector b. Okay, does that make sense? So this is a bit of a weird example here. I'm asking you to interpret geometrically what the kernel of T is, right? So in this case, you first have to figure out that the only place that actually mattered in your formula here was your x dot b, and if that equals to 0, that implies x is perpendicular to b, and so it must be some plane with the normal b. Okay. The next thing that closely relates to kernel is nullity. I guess the short interpretation of what nullity is simply that it's a dimension of a kernel, right? So if your kernel space, let's say, has 5 vectors in it, then your nullity is 5, right? It's simply the number of elements or the dimension of your kernel. Okay. So let's have a look at an example here. In this particular example, this first time we do it, we'll just be focusing on part A and this part. And after we go through image and rank, we'll come back and do this, and finally we'll do D in the end as well. Okay. So firstly for part A, well, let's firstly read the question. So let B be that matrix, and let this here be the row reduced form of the augmented matrix B augment the identity matrix that's 3 by 3. Okay. So basically it's like you just set this matrix here against that, and then you row reduced and you end up getting this. Okay. So find a basis for the kernel of B. Okay. So recall that the kernel is basically any vector where if you, in this case, let's say any vector x, where if you have B of x, it sends you to the 0 vector in the codomain. You basically want to find a basis for all these vectors x, or like this set of vectors x. Okay. So the way we're going to do this is we're going to observe that column 3 and 4 in the above matrix U is not leading columns. So let's have a look. If we have a look at our matrix U here, in particular the left-hand side, the right-hand side is not much of a concern to us at the moment, but the left-hand side, you have this matrix here. Okay, and you can see that these two are leading columns, but these two here are not leading columns, correct? And that would mean that these two columns are the two columns you can set as being free parameters, and then these two columns here are the ones that will be fixed once you set your two free parameters here. And so we'll do that by choosing to set x3, which is the variable in the third column, to be alpha, and x4 to be the variable in the fourth column and set it to be beta. Once we have x3 equals alpha, x4 equals beta, then we can go and do backsub to find out what x2 and x1 are. So this first line here, 4x2 plus 5 beta, comes from this row, right? You have 4x2 and then plus 5 beta, because this 5 here is in your fourth column. And you're setting this against 0, okay? Because remember, we're trying to find anything that sends us to the 0 vector, okay? So I guess in a sense, you can kind of ignore this stuff at the moment and just treat it as if you had 0, 0, 0 here, okay? So that's where your first line comes from. Your second line, hopefully you guys can see already, would be some sort of like x1 plus 2x2 plus 3 alpha plus 4 beta equals 0. And that would come from this row here, because you have 1x1, 2x2, 3 alpha, 4 beta. Okay. Yep, and that's exactly what we have here. And so we have our two simultaneous equations. If we just solve it simultaneously, you would firstly get x2 equals to negative 5 beta on 4, right, from this line here. And if you sub that into this equation here, you should end up getting x1 equals to negative 3 alpha minus 3 and 3 beta. And of course, x3 is alpha, x4 is beta. And so we're practically done, because now any vector in the kernel can be expressed as these three parameters alpha, beta, times by these two particular vectors, right? So you have alpha and beta here. And then when you set these two vectors up, how you get it would be, firstly, x4 equals beta. So that's why in this fourth position here, you have 0, 1, because you want just beta. You don't want any alphas. In this third row, you have 1, 0, and you get 1, 0 because x3 equals alpha. You want just one alpha and no betas. This second row, you get 0, negative pi, and 4, and that's because x2 equals negative 5 on 4 beta. You don't want any alphas, you only want negative 5 on 4 betas, and so on. Okay, and so you get these two vectors, and you can then say that this would form the basis for your kernel. Okay. And furthermore, for part C, recall that question was what's a nullity? And just like we just said, nullity is just the dimension of your kernel. And so if these are the two vectors that form the basis for your kernel, well, then your dimension of your kernel is 2, and so your nullity is 2. Nullity of B is 2. Okay. Let's keep going. If there's no questions about this kernel nullity. The next thing is image. Let T be the mapping from B to W, and it's linear. Then the image of T is a set of all function values of T. So it's kind of, in a sense, you can think of it as being opposite to your kernel. Your kernel is anything in the domain that sends you to the 0 vector in the codomain. The image is basically anything you can possibly get out of plugging into your transformation, right? So you if you have a look at the definition here, the image of T is, I guess, any element lowercase w in the codomain uppercase W, where this W can be obtained by just plugging in some vector V from uppercase V, right? So it's just saying W is just any possible vector you can obtain from T or V, where V is just some vector in your domain capital case V, okay? Right, so it's just any function value you can obtain. It's basically what the image is, okay? So in a sense, you can think of it as image corresponds to the range of a function, okay? And I guess one other important thing to note is that, again, kernel is part of your domain, image is part of your codomain, okay? The other thing that closely relates to image is rank, similar to how nullity relates to kernel. nullity told you what the dimension of your kernel is. Rank tells you what the dimension of your image is. Okay, I guess that's a very shorthand way of explaining what rank is, right? It's just a dimension of your image, whether we're looking at a matrix or a mapping T. Okay. All right. So let's go back and look at this question again. And this time we'll focus on B and this section here. Okay. So find a basis for the image of B. Again, you look at U, and previously we just said that in U, columns 3 and 4 were non-leading, and columns 1 and 2 were leading. So this time we're going to use the fact that columns 1 and 2 are leading. Okay. So since columns 1 and 2 are leading, the first and second column of your original original matrix B would form a basis for your image of B, and that follows by linear independence, right? Because if these two are your leading columns, then hopefully you guys should know from the stuff you guys did for linear independence in the previous part that since these two things are leading columns, they're both linearly independent, and these non-leading columns are dependent on these two columns. And so if anything, the only two columns that matters would be the first two columns, because these two vectors here, I guess, don't really contribute to what sort of vectors you can obtain through this transformation B here, right? Because anything that these two vectors does can be just expressed as a linear combination of these first two vectors, okay? And so that's why you have a very shorthand way or very fast way of finding out a basis for its image. You simply figure out what are the leading columns, and then you just extract those two columns out, and that is good enough to form your basis, because these two columns here don't really matter because they can be expressed in some way from your first two columns here anyways, okay? So that's why your basis for your image of B will just be the set containing these two vectors, and these two vectors, if you recall, are the first two columns of your original matrix B. 1, 2, minus 1, and 2, minus 4, 2, okay? Now, for part C, what is the rank of B? Well, just in the same way we found out what the nullity was, we just look at how many vectors are in the basis for the image. In this case, there's only 2 vectors here, and so your rank of B is 2. Okay, and that's it. Okay. Now, finally, we're going to have a look at part D. Oops. So part D asked us, without solving, does the equation bx equal to 1, 0, 1? This transpose sign is basically saying we look at the vector 1, 0, 1, column vector 1, 0, 1, have a solution and give a reason. So the answer is no, and you can have a go at this yourself because it's not exactly relevant to the topic we're going through right now, but it's basically a revision on determining the number of solutions when solving an augmented matrix. Okay. If you notice, 1, 0, 1 is the same as E1 plus E3, so the first basis vector plus the third basis vector. That's a bit of a hint because you can try apply that to the matrix U here. Okay. Yeah. And basically, in the end, you're just left with checking the conditions in this last row here, because again, this is just some revision. But if you recall, when you have 0, 0, 0, 0, you'll need some pretty specific conditions in order for this thing to have a solution. Okay. Okay, so to summarize, to find the rank and nullity, the nullity, in terms of, I guess, like for a matrix, it's just a number of non-leading columns, right? So that's what we can infer from what we have just done. If the nullity is the dimensions of your kernel, and you figure out your kernel from the non-leading columns anyways, then the nullity is also similar to just saying the number of non-leading columns. The rank of A is similar to saying the number of leading columns then, okay? Because if your rank is just your dimensions of your image, and your image comes from your leading columns, then your rank could just be the same as the number of your leading columns. And furthermore, to find a basis for your kernel and to find a basis for your image, to find a basis for your kernel, you augment it your matrix against the zero vector, so 0, 0, 0, like no matter how, I guess, how big your matrix is. And then you reduce it and backs up, okay? For finding a basis for your image, that's much easier. You just reduce it, find out which columns are leading columns, extract those particular columns from your original matrix, and you're done, okay? This leads us to the rank nullity theorem. Hopefully, this flows well from the fact that we just briefly mentioned this, okay? I guess we can think about it just from here to begin with. So for rank nullity theorem, if nullity A represents all the non-leading columns and rank represents all the number of leading columns, then clearly if we add your nullity and rank together, that should give you the total number of columns in your matrix, correct? Because every single column in a matrix has to either be leading or non-leading, right? There's no other type of columns, right? So that kind of flows well into our next theorem, which is rank nullity theorem, which basically says the rank of T plus the nullity of T, where T is a map from V to W, always has to be equal to the dimension of your domain. Or in matrix term, like I just said, rank of A plus nullity of A always has to equal to the total number of columns in your matrix A, okay? And so I guess a quick example here, if T is a map from Rm to Rn and has rank K, state the nullity of T. Well, we know that, well, like now we know this theorem here, rank K, so we have K, plus the nullity we don't know, has to equal to the dimension of your domain. Well, your domain is Rm, so it would be M, and so your nullity of T would just be M minus K. Okay, that's just a really quick example. Let's have a look at a slightly more complicated example here. Consider your matrix A and the mapping T from R3 to R3 defined by Tx equals to Ax minus 2x. Find the matrix B for T such that Tx equals to Bx. So they kind of want you to just simplify this a bit. They don't want Ax minus 2x. They just want one matrix times the vector x. Okay. Hopefully you guys can already see what you're going to do in question 1, but it's really just factorizing x out. I'm just doing that. I just factorize out your x. Here I have the I here because remember we're working with matrices. So if I factorize x out, this 2 can't just suddenly become a constant magically. It has to still be some sort of matrix. So you have A minus 2 times the identity matrix. Okay, and that's your matrix B basically, right? That's what you'll see in the next slide here. You just end up with B equals A minus 2I. You take your matrix A, subtract off 2 times the identity matrix, and you end up with this matrix here. And so this is the matrix for B. Okay. Question 2. Oops, what am I doing? Question 2. Explain why negative 3, 0, 1 belongs to the kernel of T. Remember, in order for something to be in the kernel of T, it means that when you place that in your mapping, right? So it means that taking T of negative 3, 0, 1 will send you to the 0 vector in the codomain. That's the way we're going to use to prove that it belongs in the kernel. We're going to transform this vector negative 3, 0, 1 by this particular mapping B or T, right? B is now the matrix representation of T, so we're going to evaluate B of this vector, and that should send us to the 0 vector. Okay, so let's have a look. Yep, so T evaluated at this vector equals to B, the matrix B, times by your vector. This is just row times column, right? First row times column would be negative 3 plus 0 plus 3 gives us 0 back. Every row here is the same, so you get 0, 0, 0. Okay? And so by definition, this vector belongs in the kernel because it sends you to the 0 vector in your codomain. And the final question here is write down the rank and nullity of T. Okay. Well, if you observe the matrix representation B here, you should realize that these 2 rows here are the same as the first row. So if you were to row reduce it and find its kernel, these two rows here would just disappear, right? If you row reduce. And so instantly you can see that, okay, there is one leading column, two non-leading columns. So your rank must be 1, nullity must be 2. And again, if you think about it in the sense of rank nullity theorem, once you found out that your rank was 1, you could have just done 3 minus 1 equals 2, because there's 3 columns in your matrix here. So 3 minus your 1 leading column would give you your nullity. And that is exactly what we have here as well. Okay. It's something that's a bit extra. That's not really what the question asked for, but we have a look through anyways. If you wanted to find the basis for the image and the kernel, so to find the kernel, that's the more difficult one. That's the one where you have to identify what are your 3 parameters, do back sub, and then to get your kernel. And your image is the one where you just extract out a column. Okay. So firstly, for kernel, if we go back to our matrix down here, whoops, that's not the eraser. The eraser is here. Okay. If we go back to this matrix here, after we have row reduced our matrix representation B, we were left with this matrix here. And so clearly these 2 columns here are non-leading. So we'll set x2 to be alpha. And we'll set x3 to be beta. Okay. Then our equation from our first row here should be x1 plus 2 alpha plus 3 beta equals to 0. Okay. And that should be what you see in the next slide. Here they use lambda and mu instead, but same thing. So x1 plus 2 lambda plus 3 mu equals 0. You rearrange it to get x1 equals negative 2 lambda minus 3 mu. Then in this first row, you have 0, 1 because you want just 1 mu, 1, 0 because you want just 1 lambda, negative 2, negative 3 because you want negative 2 lambda, negative 3 lambda. Okay. And so these 3 vectors will form your basis for your kernel. Then for your image, it's simply the vector 1, 1, 1, because if you look back, this first column is your leading column. And so if you go back to your matrix B, you just extract out the first column, which is 1, 1, 1, and that's it. Okay. So that concludes that example. Let's move on to the next part. It should be a bit shorter than what we just did as well. But eigenvalues and eigenvectors. Okay. So let A be a n by n matrix and the scalar lambda from the field F, and V a non-zero vector in Fn. If A V equals lambda V, then we call lambda the eigenvalue of A and V the corresponding eigenvector of A. Okay. So what we're basically saying here is, if we transform this vector V by the matrix A, we end back up with just a scaled version of itself. Okay? And hopefully these diagrams here help you understand that a bit more. So if you see here, V1, after you apply A to it, you get AV1, which if you look at that diagram, just scaled the length by a factor of 2. Okay? You applied A to it and you got 2V1 back and you just scaled your length by a factor of 2. V2, when you applied A to it, gave you negative V2. So I guess, so in a sense, I guess it scaled you backwards, right? Like it sent you in the direction backwards. But that's still okay because that's kind of like a scale factor of negative 1. That's still acceptable. The type that is, I guess, not considered eigenvalues and eigenvectors would be the example V3. When you applied A to it, we end up with this vector here. If you compare that to this red one here, well, I shouldn't draw over it then. This original V3 here, it's not any sort of scaling by any means. It literally changes the direction by a certain rotation here, right? And so V3 would not be considered an eigenvector. And this particular lambda here, well, that wouldn't exist because it's not, like V3 is not an eigenvector, right? And so that's this kind of example of what eigenvalues and eigenvectors does. right? If something is an eigenvector and something is an eigenvalue, when you apply a transformation A to it, it would just simply scale your eigenvector by that particular factor of that eigenvalue, okay? And if it's not the case, then you have this example here, like in B3, where it doesn't just scale your vector, it literally changes your vector drastically by some sort of rotation, okay? So how do you compute eigenvalues and eigenvectors? Okay, lambda is an eigenvalue of A if and only if the determinant of A minus lambda I is equal to 0. And V is an eigenvector of A that corresponds to the eigenvalue lambda if and only if it's in the kernel of A minus lambda I. So it's the same as saying this, right? Saying this and saying this is the same thing, because recall, kernel just means some vector that sends you to the 0 vector in your codomain, okay? And one particular property is that the eigenvector can't be the 0 vector, because otherwise, then I guess it would always be in your kernel, right? No matter what your lambda is, if your V here is just the 0 vector, it will always send you to 0 vector. And that's pretty useless for us to study, right? Okay. Eigenvalues and eigenvectors. So existence of eigenvalues, that's the first theorem here. It says that an n by n matrix has exactly n eigenvalues if you count real and complex eigenvalues. And furthermore, if there are repeat eigenvalues, then you also count them according to the multiplicity. So for example, if you have lambda 1 bracket squared, you get lambda equals 1 and 1. You don't just count it as a single one, you count it as 2 separate ones. Then if you add up all these eigenvalues, or like the number of eigenvalues there are, there would be exactly n eigenvalues for a n by n matrix, okay? The second theorem here is that we have the independence of eigenvectors if there are different eigenvalues. So if a matrix A has all different eigenvalues, then each eigenvector corresponding to each different eigenvalue will definitely be linearly independent, okay? This second theorem is quite useful. This one's a bit more abstract, but the second theorem is quite useful sometimes, okay? And another thing we'll have a look at right now is diagonalization. So it says that if A is an n by n matrix with n linearly independent eigenvectors, there exists an invertible matrix M and a diagonal matrix D such that A equals M D M inverse, okay? Where D is just a matrix with diagonal entries equal to the eigenvalues of A, and the columns of M are the corresponding eigenvalues of A. So basically, a little example here, D may look something like that if you're looking at 3 by 3 matrices, and everything around it would just be 0. It's simply just a diagonal matrix, which is a bit off. It's simply just a diagonal matrix with your eigenvalues in your diagonal, and then M, and I guess M inverse, would just be the corresponding eigenvector. So if the eigenvector of the eigenvalue 1 was, let's say, 5, 2, 3, then you would write 5, 2, 3 here. If the eigenvector of eigenvalue 4 was 1, 1, 1, then you write 1, 1, 1 here. If the eigenvector of eigenvalue -7 was half 3, 9, then you write half 3, 9 here, okay? And the whole point why we want to diagonalize here is, I guess, in the next slide you'll see, it's very useful sometimes. Now, another theorem here is that A is diagonalizable if and only if it has n linearly independent eigenvectors, okay? Which is like, well, we need that for the inverse to make sense, right? Because if M is composed of the columns of, or like if the columns of M is composed by the eigenvectors, if the eigenvectors are not linearly independent and are instead linearly dependent, then M here won't be invertible, right? Because something will exist in the kernel, okay? Okay, and I guess the corollary is that if a matrix has n different eigenvalues, then n is also diagonalizable. Again, this is where that previous theorem is useful. Recall that I said if a particular matrix has n different eigenvalues, or like has different eigenvalues, every eigenvector corresponding to that eigenvalue will be different, or will be linearly independent, right? That was theorem 2 here. Okay, and so if we have n different eigenvalues for n by n matrix, that means every single eigenvector that we have are all linearly independent, and so it's guaranteed that our matrix M here will be invertible, and so it will be diagonalizable. Okay. A thing to note here is that the converse is not true. So just because you have a diagonalizable matrix does not necessarily mean that you always have n different eigenvalues. There are some cases where you have repeat eigenvalues, but it's still diagonalizable. Okay. So let's have a look at an example here. I understand that I'm going a bit over time here. It should end at 2. I'll just keep going, and for those who missed it, you can look at the lecture slides or look at the recording later. Okay. So the first example here is, consider the matrix A, -1, 3, 2, 0. For part A, find the eigenvalues and eigenvectors of A. Okay. So we're going to use what we learned before. To find eigenvalues, we look at the determinant of A minus lambda I, and then for eigenvectors, for each corresponding eigenvalue, we then look at the kernel. So first things first, we're going to look at the determinant of A minus lambda I. Okay, so -1 minus lambda, 0 minus lambda, that's the only two things that changes, because remember, I here, it's just your 2 by 2 identity matrix. Determinant, so you take this times this minus this times this to give you this. Simplify it, you get lambda squared plus lambda minus 6. You factorize it, and you end up with that, which then basically gives you your two eigenvalues, -3 and 2. And now to find your corresponding eigenvectors to these two eigenvalues, you have to go back and look at its kernel, or in other words, find vectors v such that this is true. Okay. Say for lambda equals to -3, you would have A plus 3i times your vector v has to equal to the 0 vector. Set up your augmented matrix. The way I got this matrix on the left-hand side was -1 plus 3 is 2, 3 stays the same, 2 stays the same, and then 0 plus 3 is 3. Okay? Obviously, if you reduce, this column here, this row here will disappear. And so then if you do some backsub, if you set this column here, v2, to be some free parameter t, then obviously v1 has to be -3 on 2t, because you have 2v1 plus 3t equals 0. So obviously v1 has to be that. Okay? And so therefore, your eigenvector for lambda equals -3 would just be this one, right? After you factorize out your t from your vector, you would just have t outside of, well, I guess there's an extra step here. From here, you could get this, correct? Once you factorize t out, you get -3 on 2, 1. But since t is just any scalar, I guess you can think of it, like you can think of t of having at least a factor of 2 in it. And so you just bring this half out, and you get this. And it doesn't matter, like whether you write this as your answer or this as your answer, it makes no difference, because there's a scalar t at the front anyways that scales this eigenvector proportionally. Okay. And then for lambda equals to 2, we have A minus 2i times the vector v equals 0 vector. Again, you augment it the same way as we did before. Go through a similar process, and this time you end up with, after you factorize t out, you get the vector 1, 1. And that would be your eigenvector for your eigenvalue 2. Okay. So that's how we find eigenvectors and eigenvalues. First, you find eigenvalues by calculating your determinant of A minus lambda I, and then solving your polynomial for lambda. And then you look at your kernel for each particular eigenvalue to find your eigenvectors. Okay. Now question B, find the diagonal matrix D and the matrix M such that D equals M inverse AM. Firstly, where did the question even get this from? This may look familiar, but at the same time, it doesn't look exactly the same. In the previous slide, we introduced this to you by writing it like this. We said that some matrix A, if it was diagonalizable, can be rewritten as M times D times MMS. This is simply just rearranging it, right? If you have D as your subject instead, okay? So this matrix D and this matrix M, well, like we said before, your D matrix would simply be a diagonal matrix with your eigenvalues, so -3 and 2, and your matrix M would just be the columns of your eigenvectors. So the eigenvector of 2 comes here, and the eigenvector of -3 comes here. And that's it, okay? Now, this is where diagonalizing matrices becomes very useful. When you want to evaluate the powers of a matrix, usually, if you just had the matrix A, you would have to time the matrix A by A, by A, by A, by A, how many times you need, correct? K times, let's say, right? What this is telling us is that if you are able to diagonalize a matrix, you can simplify into this formula here. So MD M inverse times MD M inverse times MD M inverse. That's just saying A times A times A times A all the way K times. But we have rewritten A as MD M inverse. The point of this is that if you look at this middle bit here of every single multiplication, the M inverse and M will always just cancel out, right? And so in the end, you'll be left with M, and then D times D times D times D times D K times, and then times by M inverse in the end. That's where you get this from. And the particular use of this is that D, raising D to whatever power, is the same as just raising the diagonals, right? Because the only elements in your matrix D is just the diagonal elements. If you raise the power of D to K, you just get your diagonal elements raised to the power of K, right? A quick example here that we can have a look at is just, let's say, A, B, 0, 0, A, B, 0, 0. So we can just quickly have a look at a 2 by 2 case. If we go ahead and evaluate this, A times A is A squared, 0 times 0 is 0, A times 0 is 0, 0 times B is 0. Similarly, this entry here is also 0, and 0 times 0 plus B times B, right? And of course, this is by no means a proof, but just to get your head to wrap around it. Basically, as long as you have a diagonal matrix, you raise its power, it's just the same as raising these elements' powers, okay? So let's have a look at an example of how we can apply this. Firstly, we have a matrix A, okay? Given the eigenvalues of A, 1, 2, and 3, explain why A is diagonalizable, all right? I'll just quickly explain through this on this particular slide. Well, if your matrix is a 3 by 3 matrix, and you have 3 eigenvalues, then by the previous theorems that we have learned, we have 3 distinct eigenvalues here, 1, 2, and 3. And recall, with every single different eigenvalue, there will be a new linearly independent eigenvector. And so since we have 3 distinct eigenvalues, we will have 3 linearly independent eigenvectors. And by definition, this means that A will be diagonalizable because there are 3 eigenvectors that are linearly independent for a 3 by 3 matrix. Okay. Part B, find an eigenvector for A for the eigenvalue lambda equals 3. Well, we'll have a quick look at that. So for part B here, well, for lambda equals to 3, we have A minus 3 lambda times some vector V equals 0, and you're trying to find out what this V is. Again, we do the same thing as what we did in the previous question. We take your matrix A and subtract 3 off the, 3 times the identity matrix. So you get 1 minus 3, 2 minus 3, 3 minus 3 in the diagonal entries. Okay? And that gives you this matrix here. And as you can see, this is a non-leading column. So we'll set x3 as our free parameter t. Okay, and if we do that, then when we back sub, you get negative x2 plus t equals 0. So x2 equals to t as well. Back sub one more time, you get negative 2x1 plus t equals 0. So x1 has to equal to t on 2. And that's where we get this vector here from. Once we factorize out our t, we can also bring the half factor with us because t, again, like I said, is just any scalar. And so we get our clean eigenvector of 1, 2, 2. Okay, that'll be our answer for B. Part C then asks you, let D be this diagonal matrix here. If you realize this is exactly the diagonal matrix for A, 1, 2, 3 are its eigenvalues. Okay, and fx equals to this particular polynomial here. Show that FD gives you the zero matrix. Now this is where we can make use of the fact that for diagonal matrices, if you raise its power, you get just its entries in its diagonal, in its diagonal raised to the same power, 6i. Okay, and this makes it much easier to evaluate. And when you do that, you end up with, well, 1, 8, 27 plus 1 cubed, 2 cubed, 3 cubed, right? And then here you have 1 squared, 2 squared, 3 squared times by 6, because there was a coefficient of 6 at the front, and so on. Right? Eventually, if you work through this, you realize you get the zero matrix, and you proved part C. Now, part D. Hence prove that f of A is equal to 0. This may seem very tedious. It may seem like, okay, we have to plug this matrix A into the polynomial now. That will take quite a while to evaluate, right? But there's a diagonal matrix D ends up with the zero matrix. We can use that fact because we can rewrite A as some matrix P or M, I'll just use M, times D times M inverse. If we use this fact, you will see that part D is actually like a one-liner. It's much simpler than what you may have thought. Okay, so for part D here, we sub in A for MD M inverse instead. We don't go ahead and evaluate A cubed, A squared like tediously. We instead just sub in MD M inverse. But by the powers of A, we would get this and this for your cubed and squared example. And then the next line, since every single one of these terms has an M on the left side and an M inverse on the right side, we'll just left factorize by M, and we will right factorize by M inverse, and it'll be given this. But this thing in the middle here is exactly what we evaluated in part C, and that gave us 0. And so you end up with M than to go and explicitly calculate A cubed and A squared. Okay. And finally, part E, well, let me show you the question first. Compute A inverse as a linear combination of A squared, A, and the identity matrix I. Okay. Again, you don't actually go and calculate the inverse. It's a much faster. D, that FA is also equal to 0 vector. Then we can form this polynomial. A cubed minus 6A squared plus 11A minus 6I equals 0. Now we just rearrange for I and then multiply by A inverse on both sides of the equation. And that's it. A cubed times A inverse is A squared. A squared times A inverse is A times A inverse is I. And that's it. Okay. Now the very last thing I'll go through, there will only be one more example after this, and that will be how to use eigenvalues and eigenvectors to solve differential equations. Given an n by n matrix, the solution y can be expressed as e to the power of lambda t times the eigenvector v. Okay, so in this particular solution here, lambda is an eigenvalue, and v here is the corresponding eigenvector. Okay, eigenvector. Okay, and so the solution to this differential equation will be this particular solution if and only if A has eigenvalue lambda and eigenvector v. And in general, of all these y's, right? So again, if alpha 1 times e to the power of lambda 1, the first eigenvalue, times t, times the first eigenvector, and so on. And you have this entire sequence here, or this entire linear combination. Okay. So, last example here. Firstly, for part A, find the eigenvalues and the corresponding eigenvectors for the particular matrix A. In the past two examples already, so I'll just quickly show you the solutions, right? You just take its determinant of A minus lambda I, and you end up with eigenvalues of 0 and minus 2. Okay, and then for the eigenvalue lambda equals 0, you get the kernel of 2 minus 2, 0 is 0. Again, this is really just the same. This kernel bit here is really just the same as saying 0 times I, v equals to 0. And you're trying to find out what v is. Like I said, this is synonymous because this v is just some vector that sends you to the 0 vector in the codomain. And so you go through those steps, and you should end up that you have the eigenvector for 0 is 1, 1. And for negative 2, your eigenvector should be 1, 2. Okay? But the whole point of this is that now for this 2 by 2 matrix, we have 2 different eigenvalues, and we have solution for part B. Okay? So part B is asking you to find the solution to the two differential equations dy1 and dy2 equals to 2y1 and 2y1 minus 2y2 and 4y1 minus 4y2. Okay, if you realize, if you set this up here, you would just have the matrix A times y1, y2, yeah, where A is the matrix 2, 4, minus 2. And so by using what we learned on the previous slide here, our general solution for part B would just be some scalar alpha 1 times e to the power of the first eigenvalue times the first eigenvector corresponding to eigenvalue 0 plus scalar times e to the power of second eigenvalue negative 2 times t times the eigenvector corresponding to the eigenvalue negative 2. Now, for some questions, you may just leave it here, depending on what the information gives you. But in this case, they also gave you some initial conditions. y1 of 0 is 2, y2 of 0 is 3, which means we can go back and find out what alpha 1 and alpha 2 is. When we use y1 of 0 equals to 2, we get 2 equals alpha 1 plus alpha 2, right? Because if you think about what's happening here, you would get y1 of 0 equals to 2 is the same as saying alpha 1 times e to the power of 0 times 1, so just alpha 1, plus alpha 2 times e to the power of negative 2 times 0, so again, times just by 1, so alpha 2 times 1 gives you 2, right? Because y1 is particularly referring to this first entry. Okay? And so you get that this first simultaneous equation. And using y2 0 equals 3, you get your second row here, which gives you your other simultaneous equation. And then you solve simultaneously, and you should get alpha 1 equals alpha 2 equals 1. Okay? And that's it. You would then have your final answer. It's the same as just 1, 1 plus e to the power of negative 2, 1, 2. Okay? If I replace alpha 1 and alpha 2 with 1, 1. Okay? Finally, find the limit of yt when t approaches infinity. Well, hopefully that is obvious to you guys now. But if this is your general solution, as t approaches infinity, this term shoots up to 0. So you just have 1, 1. And that's your answer. Okay? And that's it. Okay? I know I went quite a bit over time. So for those of you who stayed, thanks for staying. If you have any extra questions, you can ask me now. I'll stay behind for another 5 minutes or something. And yeah, that basically concludes the seminar. If you guys wish to leave, you guys can leave now. I'll close my screen share now, but I'll stay in this for a bit longer. Yep, no worries. Yep, no worries. Yep, no worries, everyone.